Albert Svent Georgi, a Hungarian biochemist born in Transylvania in 1893, first discovered biotin in 1931 in his research in egg white injury, where he isolated biotin from the liver. He also discovered vitamin C, described key reactions in the citric acid cycle, spent many years studying the chemistry of cell respiration, and discovered the proteins actin and myosin. Biotin is a bicyclic compound made up of two rings, a urido group and a sulfur group, with a valeric acid side chain. It was described by Kugel and Duveneau in the early 1940s. Biotin is water-soluble and in the B vitamin group. It serves as a major coenzyme for 5 carboxylases in humans. It is covalently bonded to these carboxylase enzymes via biotinylation, which activates the biotin and ultimately releases AMP. It is a coenzyme for various important carboxylases. Biotin is also covalently bonded to histones via a distinct lysine residue, which affects chromatin structure and mediates gene regulation. These bonds play a crucial role in the folding and unfolding of DNA and chromatin, and therefore affect DNA replication, cellular proliferation, epigenetics, and gene regulation in humans. Biotinylation of histones depends very much on the dietary supply of biotin. Gene expression in both the pre- and post-transcriptional phase may also be affected by biotin, and it appears that over 2,000 biotin-dependent genes have been found in the lymphoid and liver cells of humans and are randomly distributed in the genome. Biotin is involved in cell proliferation. For instance, cells cannot progress through the G and M phase without biotin. In cases of biotin deficiencies, cells are arrested in the G1 phase. A large amount of dietary biotin is covalently linked to the lysine residues of proteins and proteases, so peptidases in the gastrointestinal tract digest these proteins to release biositin, a biotin-lysine compound, and other biotin-containing peptides. In the small intestine, biotinidase found in pancreatic fluid and secretions from intestinal flora and the brush border membranes releases free biotin from biositin and biotinylated peptides for absorption. Intestinal biotin transport depends on the supply of dietary biotin. It is transported across the apical membrane of the small intestine via the sodium-dependent multivitamin transporter. SMVT also mediates uptake of biotin in the liver, peripheral tissues, and in renal absorption. It has been noted that the central nervous system retains much of its biotin during periods of deficiency. For instance, in rats, biotin is found in the cerebellar motor system and brainstem auditory nuclei, which links it to the associated neurological symptoms found in cases of deficiencies. In cells, 80% of biotin is found in a free form, and the remaining 20% is bound to albumin. Small quantities of biotin are stored in the liver, mitochondria, muscle, and brain. The body's pool of biotin is affected by a balance between cellular uptake, release, and incorporation into catabolic reactions. It is found mostly in the mitochondria, cytoplasm, and in tiny amounts in the nucleus. The fact that biotin is found mainly in mitochondria and the cytoplasm of cells directly relates to its role as a coenzyme for carboxylases in these areas. In healthy adults, most biotin and its catabolites are excreted in urine at rates of about roughly 100 nanomoles per day. The same carboxylases required by the human body to catabolize biotin-rich proteins are the same biotin-dependent carboxylases used by intestinal microbes. Specific bacterial genera in the large colon, like Bacteroides, Bifidobacterium, and Enterococcus, synthesize biotin as well as thymine, folate, riboflavin, and pantothenic acid. It has been suggested that the molecular structure of bacterially synthesized vitamins is different from dietary sources, so specialized epithelial transporters absorb vitamins derived from gut microbes. Since urinary excretion of both biotin and its catabolites decreases rapidly and substantially in cases of deficiency, urinary excretion may be an early and sensitive indicator of a biotin deficiency. Another indicator of a deficiency is increased excretion of organic acids, especially 3-hydroxylysovaleric acid. Indirect methods for assessing biotin status is looking at biotin-dependent carboxylases and lymphocytes. The adequate intake of biotin for an adult is roughly 30 micrograms per day, and roughly the same during pregnancy and lactation. There is no tolerable upper limit for biotin, and no toxicity has been described. In fact, amounts greater than 100 milligrams per day in those with genetic disorders have not induced negative effects, and according to Zemplini et al., doses in excess of 600 times RDA are 100% bioavailable with no signs of overdose. Biotin deficiency is rare, but in individuals suffering from gastrointestinal disorders with malabsorption, like irritable bowel disease or short bowel syndrome, or in cases of chronic antibiotic use, excessive consumption of alcohol, cigarette smoking, chronic liver disease, pregnancy, lactation, or certain medications, deficiencies can occur. In fact, it has been suggested that roughly half the pregnant women in the United States are marginally deficient, even with normal dietary intake. Individuals with specific genetic disorders also have deficiencies in biotin, but these can be remedied with supplementation. Frank deficiencies can be seen in those who consume large amounts of raw eggs and in severely malnourished children in developing countries. There are multiple signs and symptoms of a deficiency. Few of the most common include inflammation of the skin around the mouth, conjunctivitis, alopecia, skin infection, and alteration of fatty acid profile in liver and skin, even delayed development in infants and children. Deficiencies also have a negative impact on cellular and humoral immune function. Since reserves of biotin are hoarded in the central nervous system, even moderate disturbances in homeostasis can cause neurological symptoms such as encephalopathies, depression, lethargy, hallucinations, and numbness and tingling of the extremities. There are several drugs that negatively interact with biotin. Anticonvulsants may increase the requirement for biotin. Phenobarbital can displace biotin from biotindinase, altering plasma transport, renal handling, or cellular uptake. Sulfa drugs and other antibiotics may decrease synthesis by intestinal bacteria, while lipoic acid and pantothenic acid may compete with biotin for binding sites to SMVT. Good sources for biotin include cooked egg yolk, liver, pork, salmon, beans, avocados, raspberry, Swiss chard, cauliflower, and cheese. Other sources include fortified cereals and fortified grain products. A good way to supplement biotin is to take a multivitamin that provides 30 to 300 micrograms per day. In cases of biotin deficiency, one can take up to 10 milligrams per day. Biotin is used in the treatment of many disorders, like biotin-responsive basal ganglia disease, multiple sclerosis, diabetes, brittle fingernails, and hair loss. There have been studies that have shown that megadoses of biotin and niacin between 30 and 500 times the RDA may have beneficial effects in terms of glycemic control, insulin sensitivity, and anti-inflammatory properties. It's also linked with pancreatic beta cell function and associated with glucokinase. I think biotin's amazing. It improves metabolism, tissue maintenance, maintains healthy skin, and supports neurological functions in the brain. So eat up and enjoy